Here we go on 5.3. We're now solving exponential equations. We're going to focus here on solving some algebraic models as well as graphical. And especially with the graphical models, those are going to help you a lot on your diploma with any of the different chapters where you have to solve. Let's look at this first one. Solve the equation 2x squared minus x minus 3 equals 0. We're first going to do it algebraically. Actually, this reminds me of a little story here. Well, Jesus and his disciples were walking around one day when Jesus said, "The kingdom of heaven is like 2x squared minus x minus 3. And the disciples looked very puzzled, and they finally pulled Peter aside and they said to Peter, "What on earth does Jesus mean? The kingdom of heaven is like 2x squared minus x minus 3. Peter said, "Don't worry, guys. It's just another one of his parabolas." All right, let's solve that, what Jesus told us to do here. So looking at this first one, as soon as we've got any quadratic in this course, we want to equate it to 0, and then we want to factor. So let's start off with that. Take it and factor. So 2x squared minus x minus 3 equals 0. Not going to waste your time on factoring that one. It factors into 2x minus 3 and x plus 1. Whichever method you use there, no problem. And then we take each one of those factors and equate them individually to 0. So 2x minus 3 equals 0 and x plus 1 equals 0. Solve the first one, take the 3 over, divide by 2, x is equal to 3 over 2, and take the 1 over, x equals negative 1. So we've got the two answers, 3 over 2 and negative 1. So now we've got to solve it graphically. Well, in order to solve these graphically, we want to punch, if there's two sides, we punch left side and right side and find our intersection point. If we equate it to 0, we're going to graph y1 equals 2x squared minus x minus 3. Put that into your calculator, graph the parabola, and then we're looking for the zeros because we want to know where does it equal to 0. So find zeros using your 0 feature on the calculator. Before we carry any further with this exponential stuff now, we've got to go back and remind you of your exponent laws. So let's look at this. You'll want to write this on the side of your notes there. When we've got two a's, b's, m's, n's, let's look at this here. If we have a to the m times a to the n, when you have like bases and you are multiplying, we want to add the exponents. Okay, so again, I'll show you the reason why. What you've got there is you've got something, let's take an example of, just easy example, let's say 2 to the 3. If we have 2 to the 3 times 2 to the 2, that means we've got 2 times 2 times 2. That's for the first 3 times 2 times 2. Put brackets around those ones. And that shows us 1, 2, 3, 4, 5. Now we're multiplying 5 2's together, so that would be 2 to the 5. Now if we've got negative exponents in there as well, that's not a problem. All we're going to do is we're going to, again, add the two exponents together, 5 plus a negative 3, which will give us 2 to the 2, or 4. And that one we call the product law. Now if we look at the quotient law, that's when we're dividing. Same kind of thing happens. But this time instead of adding, we are going to subtract. So let's pick an example for this one here. Let's do, stick with 2. 2 is always a good base to use. How about 2 to the 3 over 2 to the 2 this time? And again, what does that mean? That's saying 2 times 2 times 2 over 2 times 2. And we got to go. 2 divided by 2. Hi, yeah, that's 1. 2 divided by 2. Hi, yeah, that's 1. So we got 1 times 1 times 2. We're left with 2 to the 1, which is the same thing as subtracting the two exponents. So in this example, when we got negative exponents as well, we're doing the exact same thing. We're subtracting the negative, not a problem. So when we're subtracting that negative, it's just like adding. So we got 5 minus a negative 3, which is 5 plus 3, or sorry, 2, yeah, 5 plus 3, which gives me 8, which is 2 to the 8. And of course, everybody knows that 2 to the 8 is 256. Now when we got the power law, or exponent of an exponent, we added when we multiplied, we subtracted when we divided. When we are power of power, we multiply those exponents together. So again, just to remind you why that's true, let's take 2 again, and let's use their example there, 2 to the 2. And squaring there tells us to do the base twice. So that's the same thing as saying 2 cubed times 2 cubed. Well, 2 cubed, we know that that was 2 times 2 times 2. And do it again. 2 times 2 times 2. 1, 2, 3, 4, 5. There's 6 of them. 3 times 2, that's 6. Now, I don't want you to do all this extra side work when you're doing these questions. I want you to use those rules all the way through. Let's get on and look at the work with this one now. So that first question in the get started, we looked at a quadratic, and we solved it 2 different ways. One algebraically and one graphically. Well, let's try to solve this one here, an algebraic and a graphical method. Well, our algebraic method that we would want to use here. We've got 2 to the x and we got 32. Well, we can solve these most easily if they both were common bases on each side. If we had 2 to the something equals 2 to the something, we would know that the exponents would have to be equal if the whole powers are equal. So that's the first thing we want to look at. Can we get them both to a common base? This was 2 to the x. Can 32 be made 2 to the something? And yep, it can. We can say that 32, okay, that's the same thing as saying 2 to the 5. So let's bring that into our equation now. So we say 2 to the x equals, well, we started with 32. So 2 to the x is equal to, that 32 was 2 to the 5. So if the left side is 2 to the x, 2 to something, and the right side's 2 to the 5. 2 to the what equals 2 to the 5? Well, the only way that that's going to work is that what has to be the 5 because the bases are the same. So we can say x equals 5. The only way for them to be equal is if the exponents are equal. And you've solved it algebraically. Graphically, we want to just take it and say 2 different methods. We could just say let one side equal y1, let the other side equal y2. So we would in here make y1 equal to 2 to the exponent of x, and I'll actually just show you how you would want to punch it into your calculator. Use that little button there, 2 to the x. And y2 equals 32. And from those two equations, and this is going to work with any time we're trying to solve graphically any equation. Left side, graph it. Right side, graph it. Find your intersection point. As soon as you do your intersection, you'll get the right answer. And in this case, x is going to be 5 when you intersect those two lines. We could have also equated it to 0, just like we did on that first question, and went 2 to the x minus 32 equals 0, and then just graph 2 to the x minus 32, and look for the zeros, or the x-intercepts of that graph. The next part of the question says, could you use those same two strategies for 2 to the x equals 12? Well, first thing is, we can't get 2 to the something equal to 12. So no, we can't do it algebraically that way. But we sure can use our graphical method. So we could graph y1 equals 2 to the x, and graph y2 equals 12, and find our intersection between the two of them. And I'll let you punch that into your calculator just to make sure that you can do this. And if we plug that in, x would come out to be approximately, they said, to the nearest hundredth, so 3.58. Now there's a question there at the bottom of your page 358 that says, is it possible for 2 to the x to be equal to any real number? Give that one a thought. Definitely in that process be thinking about domain and range and see what you can come up with. Let's look at some definitions here now. An exponential equation. Hey, that's anything that contains a power that has a variable as the exponent. If we had 2 to the, x to the 2, that's not exponential. That's quadratic. If we have x to the 3, that's cubic. If we have 2 to the x or 3 to the x, now we're talking about exponential equations. For example, 3 to the x equals 81. How do we solve that? Well, the first thing we want to do is try to get the same bases on each side there. We've got 3 as the base, we've got 81. We need to figure out how to get 81 to a base of 3. So 3 to the what equals 81 is really what we're saying. And with a little bit of guess and check there on your calculator, you can get 3 to the 4. So then that means that the x has to be equal to the 4. So our solution is 4. Now you might get some equations here that look very similar to an exponential equation, but are not. For instance, if you had something like x to the 3/4 equals, I don't know, just give any number, it really doesn't matter. Let's say 16. Actually, let's use 8 there. So what we would do in this case is whenever you have x down in the base, this is not exponential, but we have an exponent here that's a number. If we're trying to solve for the x, raise both sides of the equation to the reciprocal exponent. So for instance, in this one, we would take both sides of the equation to the reciprocal of 3 over 4, which would be 4 over 3. And this would work for any of them. Even if it's x squared, you could take it to x, or take it to 1/2 exponent on each side. That would cancel off this side here. Okay, so you would have x to the 1, and on this side you'd have the cube root of 8 to the 4. Cube root of 8, that's why I changed it. Cube root of 8 is 2. 2 to the 4, hey, that's 16. So my x is equal to 16 in this case. I know you were saying to yourself, there's got to be a question coming in here pretty quick on that bit.ly. There it is. Try it out. See what you can get yourself. And I encourage you at this point, if you understand what I'm doing, pause it. Try it yourself. See if you can get to the answer on this. Let's look at this first one. I've got 4 as a base. I need to get the other side to a base of 4, if possible. If not, I know that I can get 4 to a base of 2. So maybe I can get the other side to a base of 2 as well. But I'm first going to start with 4 and see if it works. And 256, hey, we just saw that one a little while ago. And that one is, yes, a base of 4. So this is 4 to the x equals 1 over 4, and that's to the 4. But I don't have a base of 4 on each side. I have 1 over 4 here. So I need to get it up to the numerator. So I've got 4 to the x equals, hey, to get it up, that's going to give me a negative exponent. So 4 to the negative 4. Now I've got 4 as the base on both sides. I can now equate my two exponents together. So x is equal to negative 4. Not too bad. Let's go to the next one. Ooh, they both got different things. Always look at the lower number. Don't try to go higher. Take the 27 to the 9, not the 9 to the 27. Can I get 27 as a base of 9? No, I can't. So I got to look at something I can get both of them to. Well, I can take them both to a base of 3. So 3 to the 3 is 27 to the x. And then I've got 3 squared to the 2x minus 1. And this is why I went over all those rules, because now we're going to have to use our exponent laws when we've got power of power going on here. So we've got 3 to the 3x, multiply the exponents there, equals, again we're multiplying the exponents, distributing it in as we multiply. 3 to the 4x minus 2, don't forget to multiply the 1 by the 2 as well. And now I've got a base of 3 on both sides. This 3, that's an x. I know it looks crazy, but it is an x. I can equate my two exponents together. So now I've got 3 to the x equals 4x minus 2. And now it's just a whole bunch of fun algebra. Let's solve for that x. So I can bring the 3x over here, take the 2 over there. I'm going to get x is equal to 2 there. Subtracted the 3x, added the 2 to that side. Now, how do you know that that's the right answer? Well, of course, we could graph left side, we could graph right side, and we could find the intersection graphically and say, oh, it's 2. Or we could do a verification. And this is a great method if you've got multiple choice questions. Multiple choice questions, you know the answer has to be one of the options there. So take them, plug them in for the x, and see which side, left side equals right side. So we'll do that right now. Say 27 to the 2 equals 9 to the 2 times 2 minus 1. And then plug that into your calculator. And at that point, you'd be able to say that left side equals right side. And moving right along here, we are in number 2. This is getting crazier at this point. We've got some radicals happening. Oh, they're real trying to trick us up at this point. Same process, though. We're not going to do anything different. We're still going to try to get everything to a base of 2 on both sides. That's our goal. But we've got to use more of our exponent laws to be able to do it here. So first thing, let's get this 8 to a base 2, because we got a base 2 here, we got a base 2 there, we need a base 2 here. This is not saying 8 to the 3, it's just saying 8 times. So that's 2 to the exponent of 3 though. 8 is 2 to the 3. This 3 here, that's the index on this radical, and that's meaning the index becomes the denominator on the exponent. 2 to the 1/3. Hey, now we've got like bases, we're multiplying them, we are going to add those exponents together. So we've got 2 to the x equals 2 to the 3 plus 1/3. Ay, we got to add fractions. Let's do that though. Common denominator, that's going to be 3. 3 is the same thing as 9/3. 9 divided by 3 is 3 plus 1/3. So 2 to the x equals 9 plus 1, that's 10. So we got 2 to the 10 thirds. Nice. We can only equate the exponents when we have one base equal to one base. Not when we've got two things happening. We can't start doing it here. We can't drop those bases until we have one base equal to one base. Watch out for that as you go along with the more difficult ones. Now we can say x is equal to 10 over 3. And again, you could plug it in and check left side, right side, see if you get the same answer. Oh boy, they're really trying to go crazy on this one here. We've got a lot of things happening, a lot of exponent laws. Let's start with the 125 and the 625. They both kind of look like maybe a power of 5. Let's check it out. 125, I can get that to 5 to the 3. Then we start plopping in all the rest of that jazz. We've got a square root. We've got a exponent of 2x plus 1. And then on this side, 625. Yep, I can do it. 5 to the 4. And the cube root of that baby. Now let's start working our stuff here. Working the magic. Square root. That's the same thing as an exponent of 1/2. So we've got 5 to the 3 times 1/2. Or sorry, to the exponent of 1/2, which will be multiplied, to the exponent of 2x plus 1. Oof, exponent of exponent. Nice. And third root, cube root, that's 5 to the 4 to the 1/3. And now let's multiply. Start on the inside, work your way out. Doesn't matter, start on the outside, work your way in. Doesn't really matter which way you go. I'm going to work inside out. So I've got 5 to the 3 over 2 to the 2x plus 1. And on this side, multiplying 5 to the 4/3. Got to keep going on this one. Let's distribute that in. Don't forget to multiply it to the 1. 5 to the 3 over 2 times 2. That is just 3. So we got 5 to the 3x plus 3 over 2 equals 5 to the 4/3. Finally, we got 1 power to 1 power. I can lose those 5s and just look at the exponents and say 3x plus 3 over 2 is equal to 4/3. Let's subtract over the 3/2. So we've got 3x equals 4/3 minus 3/2. Oh, lovely. We got some fractions to subtract. Common denominator is 6. So 3x equals over 6 minus something over 6. Got to multiply this one by 2. That gives me 8. Multiply this one by 3. That gives me 9. That's leaving me with negative 1/6. So 3x equals negative 1/6. Let's multiply that 3 up. Divide that 3 over, or multiply it by 1/3 to both sides. So x is equal to negative 1/6 times 1/3. So that gives us negative 1/18. And again, you could go plop that into the original and see if left side equals right side. And now we take a look at compound interest. Compound interest is an application of exponential equations and functions. It's also related back to geometric sequences and series. The two of them are really tied together. So when we go through this here, starting at $100, a 2% annual interest compounded annually. Well, after the first year, we've got the original $100 plus 2% of that $100 for the interest, which is 0.2 times 100. Or 1, how did I get to here? We factored out the 100 out of both of them there. So you can write that down beside yours. That's what they've done here, is they factored out the $100 out of both of them. It's here and it's there, factored out. Gets you to this next part. Carrying it through now. After 2 years, you're going to be multiplying by that 1 plus 0.02 again, which is now exponent of 2. So after the first year, exponent of 1, second year, exponent of 2. You could probably guess what's going to happen after each year after that. You're just going to keep putting the new exponent in all the way through. So that after 2 years, it would be an exponent of t. That's the reason. But what happens if they start throwing in the interest more often than just once a year? In this case here, we're looking at compounding semi-annually, which means every 6 months we're chucking on the interest and doing the calculation there. So what we have to do to compensate here is take the rate, and I want to know, instead of an annual rate of 2%, that's the annual rate, I want to know how much rate is there for the half a year. Well, divide it by 2. Gives me 1%. And how many times would I compound in a year? Well, I'm going to compound twice as often. Instead of just once, I'm going to compound twice. So I multiply the exponent by 2. Divided the rate by 2, multiplied the exponent by 2. Okay. And then if I did it 4 times a year, which is quarterly, which is every 3 months, I would take the rate divided by 4, which gives me 0.05, and I'd multiply the exponent by 4. You're always dividing and multiplying by the same number there. And if we compounded monthly, we would divide the rate by 12 and multiply the time by 12. And there's the formula right there that you can see. That's the formula we're going to be using for any interest calculations. Okay. Divide the rate by the number of times of compounding and multiply the exponent, the years, by the number of compounding, the same n value. And the reason why it's here in this part of the chapter is because that's exponential growth. It's of the same form of A, which is our original amount, our principal value, the original amount of money, multiplied by K, which is our base here, and to the exponent, all the same. All right, let's apply that now. So we got, well, principal of $1,500 is invested at 4% annual interest, compounded quarterly. Yeah, not too bad. To the nearest quarter of a year, when will we get $2,500? Well, first of all, start with your equation. Formula. So A equals, and you can use the AO, that's original amount, or P, either one works. 1 plus the I over N to the exponent of NT. And that's an N and a T together there. Let's fill in what we know there. And we know that the original principal was $1,500. 1 plus, now we got to use the percent as a decimal. So 0.04 over, and we're doing it quarterly, so 4. And then 4 times the T, the time. We're looking for the amount of time, so we do know the ending amount that plops in at 2,500 on this side. And now to find that T value, we could either graph the left side and the right side and find the intersection point, or I prefer to take it all to one side, equate it to 0, actually, I'm going to clean that up. Instead of going 0.04 over 4, I'm actually going to divide it, which I get 0.02, and I'm going to add it to 1. So 1.02, 1.01, let's divide correctly there, to the 4t, and make sure, always make sure, when you're going to be plugging this into your calculator, you need to have that exponent in brackets. Minus 2500. And the reason again that I prefer to use the equating to zero method and then looking for the zeros on the graph is because then you only have to look in one direction along your x-axis for your answer. You don't have to worry about your window settings as much. And so we plug that into our calculator as you see it, and we need to worry about our windows a little bit now. So let's look at the window. And we're talking about time here, so we don't need any negative time. We're just going to start at 0. I don't know what my x value is going to be. Let's just pick 15. If I don't see anything crossing the x-axis, I'm just going to expand in that direction and keep increasing my x max. Doesn't really matter what the y value is, the min or the max at all. And now we graph it. And oh, lucky for us, it is there. So we're now going to find our 0 on there. So we're way down into the negative, so we want to go up. And there it is. So enter. And go above the axis. Good, we're there. And enter. And enter. And we come up with 12.83. So our t-value is 12.83, and we want to know to the nearest quarter of a year. So you look, 0.83, the nearest quarter is 3/4. So t is equal to 12 3/4 years. Or you could put 12.75 if you would prefer. Now for this next concept, I'm not going to read through the whole thing, but I am going to bring this out here. We're talking about atmospheric pressure, which decreases 12% in every kilometer that you increase in altitude. So, and it's starting at sea level at 101.3. So what we're still using is that 1 plus the I value, just like we did in the interest formula. So as soon as you've got a question that's talking about the percent, you're probably going to be using this formula. The I value, it's decreasing by 12%, so it's actually adding a negative 0.12. So you've got 1 plus a negative 0.12, which is 1 minus 0.12, and that's where they're getting this 0.88 from. The 101.3, that's our initial kilopascals at sea level. So that's our principal amount, or original amount. You can see how they're working it through there. And this is going down. It is a decay because the value here is less than 1. So make sure that you can identify between a growth and a decay by looking at the equation. That's what this one does. And last question, let's use that newfound knowledge and let's plop it in here and do one of these questions here. Cabin pressure, an airplane, is if it's less than 70 kilopascals, they're going to get altitude sickness. So it's the nearest kilometer. At what altitude do you get 70 kilopascals? Same as always, start with your formula, which is the pressure is equal to 101.3. That's our initial principal amount. And then 1 minus 0.12, so 0.88. We got 88% remaining to the h, and that's the height. And let's plug her in. We know we're looking for 70, so 70 is equal to 101.3 times 0.88 to the h. And same thing as we've done, let's bring that 70 over, equate it to 0, and graph it. So 101.3 times 0.88 to the h minus 70. We'll graph this and we'll find the zeros of it. Alright, plugging it in, now we got to just adjust our window. I'm looking at this thing. I'm pretty sure we're not going to be going 15 kilometers high. We're not going to go below sea level. So again, I'm starting at 0. I don't think I'm going to go 15 kilometers high there on this one. So let's go with 5 and go from there. And graph it. And there it is. Oh, perfect. Worked in there. If not, then we'd have to expand that domain. And let's use our 0 feature again. And left side, that looks good. Let's go to right side. And good. And what we got? We got 2.89. So the height is 2.89, blah, blah, blah. And so that means to the nearest kilometer, we've got 3 clicks high. As always, answer your 2 questions here. What is an exponential equation, and can you tell the difference between decay and growth? And that's her.